Okay, this is a practical application of Newton's laws, and I'm going to draw my diagram. It's not the snazziest rocket ever seen, but it'll get the job done. Just flames. Okay. We know that it's 7,000 metric tons, which is 7 million kilograms. 1 metric ton is 1,000 kilograms. So it's not 2, 7 by 10 to the 6 kilogram is the mass. And we're given, so we have m equals 7 by 10 to the 6 kilogram. We have the required acceleration upward, a equals 32 meters per second squared. I omitted the extra significant figure just for space reasons there, but we should be aware of the number of significant figures in the question because that's the maximum of the number of significant digits in the answer. Significant figures actually is a better word probably. So in other words, again, we should be reminding students not to just give us the 8 digits or 10 digits that their calculator gives them, but to think carefully about how much precision did we have in the data that went into this calculation, and therefore how much precision can we reasonably give in the answer. We can't invent precision out of midair. Alright, so in this case actually there are 2 forces required. We have to overcome the weight force of the rocket pressing downward. So the engine has to be providing at least enough force to overcome the weight of the rocket, and then it has to provide, if it was providing just exactly that amount of force, then the rocket would hover. It would have a gravitational force downward and a thrust force upward exactly balanced, and it would hover. But what we want it to do is accelerate upward at 32 meters per second squared, about 3 Gs. So we want something considerably more than just overcoming gravity. So there are 2 pieces. So there are the weight force, so we'll call it Fw for weight equals the mass times g, the acceleration due to gravity. And then there is the F, let's call it accelerating force, F subscript A equals ma. This is just Newton's second law. We could put some sigmas in front of those for the sum of the forces acting and so on if we wanted to. So the overall force that we need, F total, is just the weight force plus the accelerating force, is just mg plus ma. If we wanted to, we could pull out m as a common factor. Equals 7 by 10 to the 6 for the mass times g, the acceleration due to gravity, 9.8 meters per second. Maybe we should actually add that up here. Meters per second squared, I should have said. 9.8 meters per second squared. Plus the acceleration that we want, 32 meters per second squared. Equals, and I wrote it down here somewhere, or I could calculate it. (2.9) by 10 to the 8, and it's a force we're looking for, so the unit's going to be newtons. So F total force required, 2.9 by 10 to the 8 newtons. Hopefully that's a relatively clear and relatively straightforward one.